So my name is Makhlouf Hadji, and I'm a researcher in IRT Systemics. Beaucoup plus fort, okay. So Systemics is a technological research institute in Paris, Saclay, in the south of Paris. So someone, maybe you already know this institute. So I am a researcher within Systemics. And just for your information, also Systemics is a partner of the Links Laboratory. And I am also a member of the executive committee of Links. So today I'm happy to share with you some research activities. Actually, I'm working on with my PhD students, Nizi. So thanks very much for helping to prepare these slides. I would like to make a focus on very well-known research topics and very well-known problems, which are in general resource allocation in cloud radio access networks. So I will address two problems. The first one is how to assign optimally the antennas demands to edge data centers in the context of cloud RAN. And the second topic is also a very well-known topic or problem, which is the full coverage hole in this kind of networks. Okay, so these are very old and very well-known problems, but I would like to make a focus on very interesting thing. I would like to see these problems in a combinatorial optimization point of view. That's the main contribution of this topic. Okay, so very quickly the motivation. So here, this is the outline of what will be addressed in this presentation. So the first topic is about constrained resource allocation problem in CRAN context. The second one is full coverage hole optimization, also in CRAN context. So let me very quickly give you some motivations of this topic. Actually, we are running a research and development project within our partners, Orange and Nokia, in a collaborative manner in Systemics. And we are addressing cloud RAN. And one of the tasks of this project is how to optimize things in cloud radio access networks. Optimize what? So first, we know that CRAN is seen as a key enabler for next generation of mobile networks. Okay, so this is what we are addressing this kind of topics. And this solution is a good candidate to meet the exponential growth of data traffic for tomorrow. And then also, we have some preoccupations, some objectives to be reached finally when adopting cloud RAN architecture. Very quickly, this is a very simple comparison between the actual state of these kind of networks and what will be when adopting CRAN architecture of networks. The idea here of CRAN is just to centralize the computational resources on what we name here by BBU pools. Okay, so we centralize things, and then with this centralization, we make some edge data centers. Actually, if we discuss with Orange, these kind of edge data centers can be, for example, NG POPs, okay, next generation point of presence. So the idea consists to connect this kind of antennas, so aggregate demands, mobile users' demands, to one hoster or to one edge data center to finally satisfy some latency expectations and also better manage the resource consumption in this kind of data centers. Okay. So here are the motivations summarized. So satisfy the expected strong latency and minimize the resource consumption. This is the first. I mean, it's a motivation, but also it's an objective to be attained. Okay, and for now, network operators also they would like to deploy more antennas, but to improve the quality of the service, but this can coming with important drawbacks, such as, for example, increasing anti-SAR interference. So this kind of problems will be addressed in the second topic, and the first one will be addressed as the first topic. So let me go through the first problem, which is constrained resource allocation problem. So we would like to satisfy the expected strong latency requirement or constraints and minimize the resource consumption to finally satisfy the required demands. Okay. If it's not yet clear, this picture will clarify things and give very will highlight the main ideas that will be explored after in mathematical modeling. So we suppose that we have this situation, and we in some cells we suppose we have some centralized edge data centers, and the idea consists to connect these kind of antennas, and each antenna, for example, we can suppose, so please, here we suppose that we make some hypothesis, very simple hypothesis like that. For example, we suppose that at each antenna we have a certain number of demands. Here, the demands are aggregated within each antenna. And when we would like to connect these antennas to this edge data center, we have to be sure that these demands, actually, this will be expressed by CPU cores, for example, to make things very simple. But I agree with you that we can also make things more complex by adding some new metrics to be considered in this optimization. But here, to make one more thing, to make things very simple, we consider that the demands are expressed or are provided by only CPU cores, an aggregated amount of CPU cores. So if we decide to connect these antennas to this edge data center, we have to be sure that the latency constraints are met, but also the available resources in this edge data center are also sufficient for the processing or for the computation constraints. So we start by, we put I, for example, the set of all available antennas in this region, for example. J is the set of available edge data centers. And E is a set of communication links between antennas and the available edge data centers. So this is just before giving for you a mathematical modeling. Once again,
can I ask a nice question?
Sure.
What is the, let's say, obvious advantage of this?
What? Sorry?
What is the obvious advantage of this solution? Let's say, reduce operational costs. You add distribution and then you add latencies.
Exactly. So the idea is to consist to centralize things, centralize the computation. We would like to centralize the processing asked by these antennas in the same data center. Okay.
Who wins from that? Who gains from that?
Everyone will gain from that, especially the operators, for example, because if we manage in an optimal manner the available resources in these data centers, so maybe instead of deploying 100 of edge data centers, if I centralize things like this, maybe I will just make some investments, in 5 data centers or 5 edge data centers, so it will be enough. So we have to optimize the number of these edge data centers to finally reduce the costs for the operators. And if we reduce the cost for the operators, so we suppose that finally the end users will pay less. Okay. But this will be also detailed in next slides. So once again, the objective consists to assign rapidly antennas demands to the best edge data centers available actually to host the requested demands when satisfying the expected communication latency. So we decided to represent things as follows. So in one side, we put all of the available emptiness, and in the other side, we represent the available edge data centers. So this is just an example for clarifications. Okay? So we suppose that the demands coming from these antennas are presented by CPU cores, okay? And the metric we use to characterize these edge data centers are the available CPU cores to make the processing of these demands. Between each data center and an antenna, there is a latency, okay? So the objective is how to find a matching between, or a mapping between these antennas and these edge data centers. But we would like also to reduce the total number of edge data centers that will be used to satisfy the demand. Maybe for some scenarios, maybe one edge data center is enough to satisfy, to meet all of these demands. Okay, so we represent things like this. As you can see, it's a bipartite graph. Okay, in one part we have antennas, in the second part we have edge data centers, available edge data centers, and we then start our mathematical modeling like this. Before going to how the algorithm will be applied to our problem, there is a very quick theorem or proposition. We say that the optimal assignment of the antennas demands to the available edge data centers is an NP-complete problem. So we are not going to prove this, but we give some interesting references. They already have addressed this kind of problem. For us, it's a constrained resource allocation problem, and unfortunately, is an NP-complete problem. But even if the problem is NP-complete, we would like to propose two solutions or two approaches. The first one is the best one, is the exact solution, or is the optimum among the other solutions. So this is represented by the exact approach based on an integer linear programming approach. Okay, so we formulate our problem first by giving this kind of formulation. And this formulation will be considered as a benchmark for another approximation approach based on the B-matching theory. I will explain it later also. So we get two approaches, the best one and an approximation approach that will be benchmarked by the ILP. Okay, so very quickly on the on how the ILP based approach is working. So we define its X, IG as the decision variables, which is equal to 1 if the antenna I is assigned to data center G, 0 otherwise. YG, and thanks to these variables, we will reduce the total number of edge data centers that will be used in the final solution. So this is this is important in our modeling to finally optimize things in an efficient manner. Okay, so we have an objective function. I would like its classic objective function, and we can find it in the literature in different publications. But our contribution is not there. Our contribution will come after. This kind of constraints are also very well known in the literature. I mean, the first constraint, for example, we would like to satisfy all of the demands, so we put the sum of xig is equal to 1. Very classic. We don't have to violate the available resources in each data center J, so we just put this kind of constraint.